Hi, my name is Manish Gupta, and in this video, I'm going to talk about mPLUG, which basically enables vision language learning by cross-modal skip connections. So let's understand what is the mPLUG model architecture and what is the standard stuff that people do for vision language learning and how mPLUG differs from that standard stuff, right? So typically for vision language learning or multimodal learning, for tasks such as visual question answering and so on, people would take the image part, pass it through a visual encoder, take the text part, pass it through the text encoder, and then do an early fusion. So essentially, here is an early fusion happening, and then do multiple layers of transformer on top of that, right? So that's called as a connected attention network. Now, connected attention network essentially uses a single transformer for early fusion. And the only unfortunate part is that this full attention which happens here over both visual tokens and text tokens is actually time consuming. And as we know, transformer is quadratic in nature, so therefore it's time consuming. Right? Now, the other way of basically doing multimodal learning is co-attention network, where the idea is that you essentially have separate transformer networks. There's no early fusion, so you have the visual encoder encoding the images, text encoder encoding text, and there's no early fusion. But then there is cross attention. So there's a multimodal fusion which happens both on the vision side as well as on the text side. There are two transformer networks, of course, one for vision and one for text, and then they basically have multimodal fusion going on. Now, again, full attention happens here for the vision side and full attention happens here for the text side. And then there is also this cross attention. They're all time consuming, right? Plus, the other problem with this kind of an architecture is that you have to maintain two transformer networks, which also has too many parameters overall, right? So those are the two popular ways of doing vision language or multimodal kind of pre-training. Now, what mPLUG did, so essentially, if you look at it, there are two broad problems with these, right? One is efficiency. Full self-attention on long visual sequences specifically is very expensive. And the second part is information asymmetry. Now, caption text typically what you use for pre-training such models is image caption kind of data set. The caption text is pretty small and highly abstract, while images contain detailed and diverse information, right? So now, on the other hand, so as to be able to solve these two problems, these people came up with this architecture called as mPLUG. So mPLUG is essentially a vision language foundation model for doing cross-modal understanding. And the good part is it also does cross-modal generation. Okay, so that's that. So mPLUG, now let's look at how does the mPLUG basically do this efficient and effective vision language modeling, right? So essentially, it also has this vision encoder and the text encoder, encodes them. However, rather than having either of these two architectures, connected attention or co-attention network architecture, it has this mPLUG architecture. So let's look at how does this architecture work. It basically has this text encoder, which is passed to this asymmetric co-attention kind of a layer, and there are such layers, so several such layers. Maybe imagine like 3 such layers. Okay, then I mean, of course, first of all, vision and text encoder pass their inputs to a large, block of mPLUG layers, so to say, right? Multiple mPLUG layers, so n mPLUG layers. And that's the encoder. By the way, that's the decoder part, right? So the right side is the decoder part. Remember, it is for generation as well. So this is for cross-modal generation as well. So therefore, therefore the decoder part is the standard transformer decoder. There's no change there. There's causal self-attention, cross-attention, and then feed-forward network, feed-forward layer, right? So no change in the decoder part. Now on the encoder part, you see, on the text side, you essentially pass it through many more layers compared to the vision side. That's the main difference, right? So on the text side, you basically take the text input and you have this cross-attention thing going on the text side. It basically consumes the visual input as well. And then there is self-attention, cross-attention, and feed-forward, the standard layers in a typical transformer network, with cross-attention. So that's what it does. And then after you do S layers of text processing, then you essentially take those inputs and then connect with the visual input. And then you do one layer of visual and text combined processing. Okay. So let's say you do 3 layers of text processing, 1 layer of combined processing. Then you do 3 layers of text processing, again, combined 1 layer of overall visual processing and so on. So overall, you do it for n times. Overall, you do it for n times, and that's basically your mPLUG architecture. Okay. So that's your mPLUG architecture. It's sort of a morph in between these two architectures where, you basically get efficiency because you are doing, this connected attention, but you do only once, let's say in every 4 layers in that senses, right? if basically you do 3 layers of this and 1 layers of this, right? And also it basically has effectiveness because, well, it's basically combining. It's basically doing not early fusion, but actually doing a combination of early and late fusion in some ways, right? So I mean, it's basically doing you see a cross attention as well, so which basically brings in efficiency, which basically brings in effectiveness. Okay. So now the architecture is, of course, trained on image text data using 4 different pre-training losses: ITC, mask LM, ITM, and prefix LM. So ITC is basically image text contrastive loss. So you want to ensure that the positive image text pair are always ranked higher up compared to image and negative text pairs, or text and negative image pairs, right? That's the image text contrastive loss. Mask LM, so that's masked language modeling. So basically mask out a few text tokens and ensure that you can actually reproduce those tokens at the output, right? Image text matching, so which is a binary task. Of course, mask LM is a cross entropy based loss, right? And image text matching is a binary classification loss. So given an image and a text pair, figure out whether they are basically matching or not matching, binary loss, right? Binary cross entropy. So that's basically on the 3 losses for the understanding side. Now there is one pre-training loss for the generation side, which is prefix LM. So given the image, basically predict whether you're able to you're able to generate the entire caption properly or not, and that's a token level cross entropy loss. Okay, so that's the pre-training. Now, how does the mPLUG model perform? So for doing the experiments, the basic mPLUG model, they train 2 such models, a small one and a large one. So the pre-training data is 14 million images from these 5 different data sources, which is very popular, right? MS COCO, Visual Genome, Conceptual Captions, Conceptual 12 million, and SBU Captions. For the text encoder side, so you see this is a text encoder. They used 6 layers for 6 layers of BERT base, and the remaining 6 layers of the last 6 layers of the BERT base are used for the cross-modal skip connected network at the top. Okay. So first 6 layers are for the text encoder, and the next 6 layers, or the last 6 layers of the BERT base, are basically used for this part, for the orange box there, light orange. Yeah. They also used a 12-layer transformer for the decoder. So this is a 12-layer decoder, right? 12 layers. And then for the visual encoder, they basically use the clip VIT model. So they actually use transformers for the visual encoder, also clip VIT. And then they use 2 different sizes, VIT-B and VIT large, and that gives you 2 sizes of the mPLUG model. Okay. So how does it perform really, right? So they evaluated on several tasks. I'm just putting up some of those results here. So image captioning and VQA task here. So image captioning and visual question answering task. So for image captioning, they of course compared on 2 different datasets, COCO captions and no caps, and with several different baselines, including blip, which I covered recently in one of the videos, right? And what they observed is that mPLUG model, and of course they compared on several metrics, right? Blue, Meteor, and then Cider, and then Spice, and so on. And what they found is that the mPLUG model gives you pretty good results on most of these on most of these metrics. And most of these metrics, you basically see mPLUG model gives you very good results. In fact, mPLUG model outperforms mPLUG model with the 14 million pre-training data, not the parameters. Okay, this is the data, pre-training data. Outperforms Blip, outperforms Lemon, and also SimVLM, which basically use way larger amounts of data, right? So Lemon uses 10x more data than mPLUG. SimVLM uses 100x more training data than mPLUG. Similar are the observations on the visual question answering task, where you observe that the mPLUG large model essentially outperforms SimVLM and Florence, which basically use 100x and 60x more pre-training data. Now, if you think about the inference part, right? So essentially runtime at inference, you basically observe that connected attention network and co-attention network, the 2 architectural choices that I showed to you here, well, they are not as great. They took way longer to come up with the final output, right? They're way longer, right? Compared to that, our cross-attention or cross-modal skip connected network, essentially, the mPLUG model essentially takes much smaller amount of time, about 4x smaller amount of time. So it's 4x faster. But then if you look at accuracy numbers, well, 80.45 compared to 79.456 and 79.32. So, on 2 different data sets, NVLR reasoning data set and VQA visual question answering data set, you get better results in 4x smaller time, right? Who won't want that? So that's basically, the goodness of the mPLUG model. Now, quickly to summarize, mPLUG is an effective and efficient vision language pre-training framework for both cross-modal understanding and cross-modal generation. So you can use it for generative tasks as well. Basically, it involves or they proposed a new asymmetric vision language architecture with the novel cross-modal skip connections. Right, there were cross-modal skip connections on the vision side. You have lesser number of layers on the text side. You have much more number of layers, right? And it addresses both of those problems with vision language pre-training, information asymmetry, and computational efficiency. Right. Well, they pre-trained the mPLUG model on large-scale image-text pairs, 14 million image-text pairs, and then they showed strong results on image captioning, visual question answering, image-text retrieval, visual grounding, those kinds of tasks, and which I've some of which we discussed in this video. They also demonstrated strong zero-shot transferability on multiple video language tasks, which I didn't show in this video, but you can read up more in the paper. Okay, so that's it for this video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.